Today I'm going to talk about our theoretical study on polynomial functions, modulo p to the power of e, and its application in accelerating bootstrapping. This is a joint work with Robin Hillen, Ilya Ilyashenko, and Frederick Vercauteren. So let's start by linking bootstrapping and polyfunctions. Bootstrapping is an operation in homomorphic encryption that reduces noise. For schemes such as BGV and BFV, it has two parts: linear transformations and digit removal procedure. Since the latter is 3 to 50 times more expensive than the former, we say the digit removal procedure is the true bottleneck of bootstrapping. And the main building block of the digit removal procedure is called digit extraction function, which is an instance of polynomial functions modulo p to the power of e, or polyfunctions in short. By definition, polyfunctions are just polynomial mappings modulo p to the power of e, and this polynomial is called a representation of the polyfunction. So we use uppercase letter for the polynomial and the lowercase letter for the function it represents. When e equals to 1, every function over a field is a polyfunction, and we can find the representation via interpolation method. But in general, this does not hold. So in our study, we systematically learn polyfunctions in the following way, like we answer the following questions. First, how to determine whether a function is a polyfunction. And for a polyfunction, how to find a representation of it. As we will see later, every polyfunction has non-unique representations. So how to find representations that are more homomorphic encryption friendly. By that we mean polynomials of lower multiplicative depths or requires fewer scalar and non-scalar multiplication in its evaluation. With all these insights, we optimize the digit extraction function and the digit removal procedure, hence accelerating bootstrapping for BGV and BFV. In our definition, digit extraction function maps every element to its least significant digit in the symmetric digit decomposition. And this least significant digit is again regarded as an element modulo p to the power of e. We use lowercase g with a subscript e to denote the digit extraction function modulo p to the power of e when p is explicit. Then, using our polyfunction representation terminology, this digit extraction function is a polyfunction. And previous study used different methods to find its representations. For example, when p equals to 2 and e equals to 8, Halevi and Shoup find this representation of multiplicative depth 7. Later, Chen and Han improves it with another polynomial of multiplicative depth 3. And we observe the difference between these two polynomials have non-zero coefficients, but it evaluates any element into 0 modulo p to the power of e. Such a polynomial is called a null polynomial modulo p to the power of e. In other words, if we start from any representation, adding a null polynomial to it will change the coefficients, but not the function it represents. Therefore, if we know the set of all the null polynomials modulo p to the power of e, then starting from any representation, Halevi-Shoup or Chen-Han, using this set of all null polynomials will give us the complete representations of this digit extraction function. And our idea is to select representations that are more homomorphic encryption friendly from this complete set. So the set of all null polynomials are most easily characterized in the following factorial basis. And we notice evaluating this following factorial polynomial of degree I at any integer always give a result divisible by I factorial. Therefore, if we consider the periodic evaluation of this I factorial, this number is, when this number is no lower than e, that means this following factorial polynomial of degree I is a monic null polynomial modulo p to the power of e. Otherwise, we will need to multiply some powers of p in front to make this polynomial null modulo p to the power of e. And it has been shown that any null polynomial modulo p to the power of e is a linear combination of polynomials in these two categories. So if we denote the smallest I that is satisfying this criteria with mu p to the power of e, in other words, x mu p to the power of e is the monic null polynomial of the lowest degree, then we can do the following. We start from any representation of a poly function, and then we compute the Euclidean division with this monic null polynomial x mu p to the power of e. The remainder part again represents the same function, but it is guaranteed to have degree lower than mu p to the power of e. In other words, this trick gives us an estimate of the upper bound for the lowest degree representation of any poly function. Then back to our specific case of a digit extraction function. We show that Chen-Han representation already has the minimal degree p minus 1, e minus 1 plus 1. But still, we can find representations that are more HE friendly in the sense that they can be evaluated with fewer scalar and non-scalar multiplications. Our first improvement uses the fact that digit extraction is a symmetric function. We prove for any symmetric function, it has representations that are sparse, containing only even or odd exponent terms. For example, when p greater than 2, we can start from this Chen-Han representation and we eliminate all the even exponent terms. Then we obtain this polynomial which only contains odd exponent terms. For p equals to 2, it will become more tricky, and we refer interested audience to our paper. Then using this technique, we reduce the number of non-scalar multiplications by a factor of square root of 2 and the order of scalar multiplications by a factor 2 in the homomorphic evaluation. Our second improvement uses lattice. So interpreting polynomials as its coefficient vectors, null polynomials with degree bound n forms an n plus 1 dimensional lattice. This graph visualizes a 2-dimensional lattice formed by these black dots. Then if we start from any representation of the digit extraction function, we can solve the closest vector problem to obtain the closest new polynomial OX. Their difference, GE prime, again represents the same function, but it's guaranteed to have lower L2 norm. Like the coefficients will be much smaller. So as an example, we combined the former two tricks. For our earlier example of p equals to 2 and e equals to 8, we obtain this polynomial, which only contains even degree terms, and also have smaller coefficients. This will allow a more efficient homomorphic evaluation strategy, and it leads to less noise growth. Our third improvement uses function composition. So consider the digit extraction function modulo p to the power of e when e is very large. Then it can be done in 2 steps. Step 1, we pick some lower e prime and then consider the same function g but modulo p to the power of e prime. Step 2, we consider the function g modulo the original large p to the power of e, but the relevant domain is the range of step 1, which is a subset of the integers modulo p to the power of e. So over this subset, there will be more new polynomials than over the whole set. Therefore, using the new polynomials over the subset, we can obtain a representation for the function in the second stage of much lower degree. So this method reduces the order of non-scalar multiplication from square root of e to quadruple root of e, and the number of scalar multiplication from e to square root of e. At the same time, array function composition increases the multiplicative depth by roughly log 2 p. So this interesting trade-off stops us from doing this function composition infinite times to reduce the complexity. Again, we have an example. So consider doing the digit extraction function modulo 2 to the power of 25. It can be done in 2 steps. Step 1, we use the digit extraction function modulo 2 to the power of 8. Step 2, we use this representation over the subset, which has really low degree, degree 5. And then their composition gives us the digit extraction function modulo 2 to the power of 25. Here we also combine these with the lattice trick we described before. Therefore, these coefficients are remarkably small, especially considering they are defined modulo 2 to the power of 25. Beside from optimizing the digit extraction function, we also optimize the digit removal procedure. So given an integer w modulo p to the power of e, the goal of digit removal is to zeroize the least significant v digits. And this procedure requires us to extract these digits w0 up to wv minus 1, 1 by 1. However, to control the depth of the whole procedure, we actually need to do more than v-digit extractions. For example, to compute w1, it would be natural to use the difference between w and w0. but W0 already costs high multiplicative depths. So it's much wiser to use the difference between W and this W01. So computing W01 will cost less multiplicative depths than computing W0, and its second least significant digit is already guaranteed to be 0. That means it's sufficient to for the extraction of the W1, the second least significant digit. Similarly, for all the other expressions, they are used to extract other least significant digits while controlling the depths. So in compared to other Halevy-Shoup and Chen-Han digit removal, our realization of the digit removal procedure has 3 main differences. We exclusively use our optimized representation, and we reuse these representations as much as possible. We also evaluate multiple polynomials simultaneously using the baby step, giant step technique. Now I'd like to show some experimental results. So First, when E is low, here we choose E as 15, 6, and 4, then we apply all our optimizations except the functional composition. Then when P equals to 2, zeroizing the least significant 7 digits out of 15 in our digit removal procedure with our optimization results in a factor of 2.6 speedup in the packed bootstrapping in compared to the state of art. Moreover, when E is large, we also test our function composition method for digit removal. So when P equals to 2 and E equals to 59, in the first step of the digit extraction function, we choose this E prime to be 16. At the end, we get a speed of 2.8 for the digit removal procedure. In conclusion, we speed up the bootstrapping for BGV and BFV by optimizing the digit extraction function and the digit removal procedure. All these optimizations are possible due to the existence of non-trivial null polynomials modulo p to the power of e for all the polyfunctions. We believe polyfunctions modulo p to the power of e are also of independent interest, and we look forward to more applications in cryptography. Thank you for your attention, and I'm happy to receive any question.